Given a rooted tree with n nodes and an edge list, rooted at node 1. Assign each edge weight 1 or 2. Path cost is the sum of edge weights along the path. Pick any deepest node x and count how many assignments on the path from 1 to x make the total cost odd. Return that count modulo 10 to the 9th plus 7. Example 1, edges connect 1 and 2. The path from 1 to 2 has a single edge. Weight 1 gives odd cost 1, weight 2 gives even cost 2. Only one assignment works, so the output is 1. Example 2, the tree has maximum depth 2, nodes 4 and 5 are deepest. Take the path 1 to 3 to 4, 2 edges. Weights 1 2 and 2 1 both sum to 3, which is odd. That gives 2 valid assignments, so the output is 2. The problem statement wraps itself in tree terminology, but it asks us to pick a single target, any node at the maximum depth. By running a simple depth-first search from our root node, we can calculate the tree's maximum depth. Once we locate our deepest path, every other node and branch becomes completely irrelevant. All we care about are the exact number of edges, m, that bridge our root to that single deepest leaf. We are required to assign a weight of either 1 or 2 to each edge in this path so that the final sum is odd. Let's look at how these choices affect our total. Adding a 2 to our running sum does absolutely nothing to its odd or even nature. The only choice that can actually flip our path's parity from even to odd, or odd to even, is assigning a weight of 1. This means we have total architectural freedom for almost the entire path. For the first edge, we can choose a 1 or a 2. For the second edge, we can choose a 1 or a 2. We can continue making independent choices for every single edge up until we hit the very last slot. For these first m-1 edges, each edge provides exactly 2 options. What happens at the final edge? Our hands are completely tied. If the sum of all previous edges is currently even, the final edge must be assigned a 1 to force the total to be odd. If the previous sum is already odd, the final edge must be assigned a 2 to keep it odd. No matter what choices we made earlier, the final edge has exactly 1 valid assignment to satisfy our constraint. Because the first m-1 edges give us 2 independent choices each, and the final edge's value is always strictly forced, the total number of valid assignments is simply 2 raised to the power of m-1. Our entire algorithmic pipeline reduces to identifying that maximum edge depth m and computing this modular power of 2, completely bypassing any manual graph exploration or combination counting. We begin our solution by calculating the maximum edge depth of our tree using a standard traversal. Once we have the total edge count of our longest path, we decrement it by 1. This leaves us with the exact exponent value we need to compute our combinations. Before we write the math loop, beware of a major language trap. In languages like Java, it is incredibly tempting to use the standard library shortcut math.pow. This fails completely. Math.pow operates on floating point doubles, which lose precision entirely once the number gets large, leaving you with rounded, broken values before you can even apply the modulo constraint. To calculate this safely without overflow or precision loss, we must implement direct modular exponentiation. We initialize our running result to 1, set our base to 2, and hardcode our primary prime modulo configuration. We process the exponent using binary exponentiation. In each iteration of our loop, if our remaining exponent is odd, we multiply our base into our result and immediately apply the modulo. Then, we square our base, apply the modulo again to keep the number bounded inside memory, and cut our exponent in half. This ensures our calculations stay perfectly accurate inside integer limits. Once our exponent loop hits 0, our result register holds the exact, uncorrupted modular score. We return the value, giving us a clean, robust solution that runs safely across any scale. Let n be the number of nodes and m the maximum edge depth from the root. Time is O of n plus log m, depth first search touches each edge once, and binary exponentiation halves the exponent each loop step. Space is O of n for the adjacency list, plus O of h for the recursion stack, where h is the tree height. Define the main function with the tree edge list. Find the longest root to leaf path length by calling depth first search from the root. Set the exponent to max depth -1, matching our combinatorial formula. Start the running product at 1. Use 2 as the base we will repeatedly square. Keep every intermediate value inside the problem modulo. Loop until every bit of the exponent is processed. When the lowest bit of the exponent is 1, include the current base in the product. Multiply result by base and apply the modulo filter. Square the base and reduce again so numbers stay bounded. Have the exponent, dropping 1 bit each iteration. Return the accumulated count of valid assignments.